Dear all, welcome to the week 11 live session discussion on molecular spectroscopy of physical chemist perspective live discussion session. I am Marco Prabhu Chaudhary. Today I will discuss some of the topics discussed in week 11 and week 12. And now week 11 I have discussed the last time. Today I will discuss the three lectures are covered by Professor Datta. Week 12 where he taught about some NMR techniques, how to get the NMR spectra and spin relaxation processes or spin lattice relaxation processes. I will not go to the deep, but I will today I also try to solve the week 11 assignment problems and some of the other numerical problems from the physical chemistry Atkins book. Okay, so let's start. So let's recapitulate about something the last week we have covered about the basics of NMR spectroscopy, where it's the NMR activity will be there for those nuclei for which the nuclear spin is non-zero. Obviously, for atomic for even atomic mass like an even atomic number like 16 oxygen or maybe 12 carbon, that the nuclear spin is zero. So that is an NMR inactive molecule. And for nuclei like 14 and 10b, these are having even atomic mass but odd atomic number. So they have integral nuclear spin, whereas odd atomic mass nuclei like 13 carbon or proton NM1H. These are the two mostly used NMR techniques, as you already know. These are some NMR active nucleides. So these 13C and 1H, they have the nuclear spin as half integer or half. You know that the half is actually ace. That is the quantum number, nuclear quantum. But ms value, depending on the ms value, plus half and minus half, that is alpha and beta spin. So both have spin value is half, but ms is plus half for alpha and beta minus half for beta. Now, now when there is no external magnetic field is there, so that time alpha and beta, these two are degenerate spin states. But now when you give some magnetic field per se along z axis of then there will be splitting between this alpha and beta spin, and the gap is depending on that magnetic field, how much magnetic field you are giving, depending on the splitting will be different. Splitting will be different in the splitting energy will change. So as you can see, the energy is gamma h cut and b naught is your magnetic field along the z axis, and alpha will be stabilized and beta will be destabilized by the similar amount. And here are some of the numerical relationship I have given here. I think in the next discussion series we will discuss some numerical problems from the NMR spectroscopy, which may come into the CSI net or something like that. It may help you, or even in the upcoming exam for this course. Now, next we have discussed that what are chemical shifts and what is the effect of electronic environment in shielding the nuclei from the external magnetic field, and what shielding and deshielding is. And we have also discussed that what kind of reference we use in a NMR spectroscopy, like we use trimethylsilane TMS in proton NMR as a reference. And we mainly discussed that, and about what is the coupling and why what is the quantum mechanical treatment behind this coupling, that we always know that individual proton is means splitted into some lines by other protons, nearby protons, or if it will get coupled by the equivalent proton or not. So that we have discussed. So let us recapitulate very fast that what has happened, that suppose uh, in a new in a system like AX system means your both are proton, A and X both belongs proton, but they are having some non-equivalent electronic environment. That's why they are denoted as A and X. So there is some difference between them, and they are at some distance. And First, we have discussed when there is no coupling. Here the coupling will be treated as a perturbation, first order perturbation. But suppose there is no perturbation or no coupling, so how the spin will reorient them, how the spin states are looks like, that we will discuss. So the first will be the here are the we have discussed that these are four states that can be possible: alpha A, alpha X, both for alpha, and for alpha A, beta X, psi 30, alpha X, beta X, or psi 4, beta A, beta X. So why the psi 2 have alpha A, not alpha X, that we have discussed, because we have taken the shielding constant as the for shielding constant for A is less than X. So the it will A will experience much more magnetic field, so splitting will be more, so alpha will be stabilized more. So that's why alpha A is taken as a means the uh, second wave function that has a lowest energy, the higher energy than alpha A, alpha X, but lower energy than alpha X, beta A. Now the Hamiltonian is already there. We know that it is gamma, beta naught, and then your shielding constant, those things are coming into place, and then your angular momentum is there. So based on that, we have calculated the energies for these spin states, and we have found that these are almost similar. That energy of 1 and 2 are 1 and 4 are almost similar, but there is a change in the sign. And similarly for alpha 2 and alpha, energy of 2 and second and third has almost similar in magnitude, but there is a difference in negative sign. And we have then means shown you that here only the change in the spin states happening like that. It is going, if it is going from the first to third, then there is a change in the alpha to beta spin of A nuclei, and if it is going from 1 to 2, then there is a change in the spin for X, going from alpha to beta. Here, like, there are two two transitions are possible, four transitions are possible, but two are having equivalent energy. So that's why we will see two kind of lines for each one for A and X having similar intensity, because both has similar number of transition. Now why the we will expect A to be deshielded more than X, because we have already known that the shielding constant for A is less than the X. That is all coming from. And then we have introduced the coupling, the perturbation as a first order perturbation, and we have find out that both 1 and 2 energy, means the energy levels, they have they will destabilize by the same energy, that is 8jx by 4. At the same time, the second and third will be get destabilized, sorry, the first and second will get destabilized by 8jx by 4, that amount is same, and for second and third will get destabilized by the similar energy. And that is why what you are expecting, that now your earlier you suppose when there is no coupling, you expected that for A you will get one line, for X you will get one line. Now as we have introduced the coupling or the perturbation, you can say, now what you are going to expect, that your suppose this was the earlier case where you had A and X. Okay, suppose this is your delta chemical shift going from, this is up shield, means shielded, and this is deshielded, right? Much more. Okay, now what you are going to see, I will use another ink for this. So for X, eh, you are now you are going to see four different transition, and for X, suppose it was something like 1 to 2 was for X, and um, 3 to 4 was for X. Now you will see that for 1 to 2, right now what has happened that the energy, for one, the energy has changed by 8jx by 2, decreased, and here the energy has 3 to 4, the energy has increased by 8jx by 4, which you can see in this spectra as a two lines equivalently spaced from the earlier line what you have expected if there is no coupling, and the gap between the expected one and the new formation line was JAX by 2, and the gap between two lines now is JAX, which is the coupling constant. And similar thing you will expect for A also. Interesting thing is that now earlier it was the intensity of those line will also decrease. Okay, so that you will expect. So you are going to get doublet instead of singlet for these cases. Now this is one case where you have chosen a non-equivalent protons like AX. Now what has happened to A2 system? A2 system means both, now we are not choosing two different kind of nuclei or two different kind of protons. Now you are taking a nuclei with the same equivalent condition. Let me check if my audio is working. I hope so. Let's check. Yeah. Now, okay. So now for A2 system, we have found out that the firstly the similar thing we will do what we have done from the AX system, but here the Hamiltonian changes a little bit, not much. Here instead of 2A, we will write something about the angular momentum as IA1 or A2, or you can say IZ1 or IZ2 for because we are choosing only the Z component of the angular momentum, right? Because the external magnetic field is oriented along the Z axis. Now we got the energy levels when there is no coupling, of course. Now, and here one more thing I have missed out, that the here the wave functions looks like something like alpha 1 and beta 1 beta 2, but in between the second and third having both alpha 1 beta 1, but as they are indistinguishable cases, you, you have to take a linear combination of both alpha 1 beta 1 minus alpha 2 beta 1, and one is alpha 1 beta 1 plus alpha 2 beta 1. Now you will see that for the first case, a first and fourth case, they will have some energy. But the magnitude is same, but there is a difference in the negative sign only. And in case of psi 2 and psi 3 naught, you will see that both will have energy at 0. Right? So you can take that as a reference point, and then when you introduce the coupling, you will see here that your 1 and 2 both will get destabilized similarly, HJ by 4 amount, and HJ1 and the second and the third. The second was actually stabilized by minus 3 HJAA by H cut. Here the thing we have got last time. It looks a lot of calculation. Actually, the calculation was a lot, but calculation was easy because most of the cases you are going to get 0 because alpha 1 beta 2 alpha if they are not an eigenvalue operation, you are going to get for different I1x I2x after operating those operators on your wave function. And for 3, you have seen that it was destabilized by HJ by H cut square. Actually, HJA by 4 actually. I have written it incorrectly. Here also I think I should have written 4. Okay. Now, here is the situation. You can see this portion now. When there is no coupling, it has some energy, and it has a 0, 2 and 3 were degenerate. They were at 0 energy, and 4 had some energy. And you can see you expected only two transitions, right? Now for A and X. Now what has happened that after the thing has done that your 1 has been destabilized by 1 and 4 was destabilized by 8JA by 4, and 3 also got destabilized by 8JA by 4, but the third one destabilized by 3JA by 4. Now when you are going to see the transitions, you also have to include two things. Earlier you were using a one photon rule, but now as those are equivalent protons, you have to also consider about the spin multiplicity. So that rules, the spin rule coming into place, the spin multiplicity, that your change in the spin multiplicity should be 0. So there should not be change in the spin multiplicity. Now you can see that your first and the fourth one are symmetric spin, means though those are in triplet states, and your third one is also a triplet one. But your second one, the spin for that minus alpha 1 beta 2 minus alpha 2 beta 1, that is an antisymmetric speed. So that belongs to a singlet state. So you can see that you cannot involve second into any transition, the second state. So you are going to expect only for the triplet here the transitions for 1 to 3 or 1 to 4 or 2 to 3, something like that. So but again, you can't expect 1 to 4 because that will get that will be problematic because of that one photon rule, because you cannot really change two photons, two spins by one photon. You will require two. Now as you can see that now you have only two transitions again, that is 1 to 3 and 3 to 4, and as in all the cases 1 3 and 4 all got destabilized by hj by 4, so their energy difference will also not change. So because of that, uh, even if the coupling is there, you can't really see any change in the NMR spectra. So you can't really see from singlet to doublet, but the coupling is there. As all of them got destabilized by the same amount, that is why you can't see anything there. Okay. So now what was next? So similarly for this was AX or AA system. Now for AX2, or what can we expect for a AX3 system? So as you know, it will follow a Pascal's triangle if your that 2ni plus 1 if I is half. So we are going to get a problem from the assignments where I is 1 actually. So we'll see what will happen to the intensities, but still regarding the number of lines, you can see for AX2 you expect that your X will be doublet because of coupling from the A. So but A will, for A what will you expect, what kind of lines you can expect? The fast X will, there are two X, right, AX2. So the fast X will um, split your A into 2, that is 1 is to 1. Now those two lines will again be splitted twice individually by the second X. So ultimately you are going to see that you are going to have three lines having 1 is to 2 is to 1 for proton, as we are discussing for protons. So you are going to expect a Pascal's triangle, but where the I will be more than half, then you are going to have a different intensity ratio. Anyway, the ratio, the gap between the multiplates will be your coupling constant JAX, or that is, and the same will be there for the X line also. And for AX3, you have to do the same. X will get splitted into twice, and for A, the fast, it will be a doublet, then doublet will again be splitted into a triplet, and triplet will again be splitted into a quadret of a ratio of 1 is to 3 is to 3 is to 1. So what will happen if you increase the magnetic field? Do you expect your coupling to increase? Actually, no, because your magnetic increase of magnetic field will going to, so you will have a greater gap. Actually, not the gap. If you go by the energy scale, the gap will be there. But if you choose a delta scale, then there will be no change in the then there will be no change in the uh, 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 gap between the A and X. So if you take your ethanol spectra, 1H NMR spectra for ethanol in 300 megahertz instrument or a 600 megahertz instrument, the peak will come in the same place because you are using a delta scale. Delta scale will, the chemical shift come in the ppm, right? So that we take for normalize, or you can say so that we can get the similar uh, value of chemical shift uh, for different instrument also. Okay, now we'll come to the 11 week 12 lecture. What was covered by Professor Datta? We'll discuss this very briefly. That the first thing is that was discussed that how NMR spectra, how NMR spectra is being recorded. Is being recorded. So there are two processes mostly. One is using your continuous wave. Another is pulsed wave, right? Wave. Another is pulsed. Now, wave means here we are talking about the radio frequency, because the energy gap are very less here, even lesser than, I guess, the even lesser than the rotational levels we are discussing here. Okay. And now these continuous wave, there are two cases. As you already know, your alpha beta were first degenerated and degenerate. Now when you apply your external field, so depending on your external field amount, see, for a the much external field you will give, there will be much more splitting between the alpha and beta. Your beta will be here and alpha will be here. Now if you increase a much more, so if you increase the B and uh, see the resonance between and apply your radio frequency new L constant, and B you vary. Another method would be B to be constant and you vary your radio frequency. Mostly, this method is a conventional method, but in means, today, in most of the NMR spectrophotometers are actually using FT NMR, using pulsed wave, pulsed radio wave, where the spectra is recorded as in time domain. Actually you are going to get FID file. That FID file you actually generate in a machine language, that is an I think free um, intensity decay, something like this FID file. Now when your actually induction file, I okay, FID file. Now this FID file actually get you is Fourier transformation to get this thing in frequency domain, which we are most familiar with. Yeah, suppose if you get an oscillatory so what happens actually for time domain, you get all of the decay at once. Then what is the advantage? You get um, um, good signal to noise ratio. You get uh, means in an instant of time you get all the means information of the system. And using this pulsed wave FTNMR, what you can do, that you can do much more applications like 2D NMRs. Those you can uh, carry out, which was not possible using the continuous wave method. Now you have also learned that how to record the NMR spectra, that what is bulk magnetization, right? So you have learned that um, this when a magnetic field is given, so based on that population of alpha and beta, you are going to get that your aim is going to be dependent on the I alpha by I beta, and you have found out this is actually something 000 something 6 8 or something like that. I don't exactly remember these places, the decimal places, but actually it was not one but more than one. And when there is no other external field, or I mean, no other field is given, only the external magnetic field is there. So then your bulk magnetization vector and your beta, which is B, that is your magnetic field working in the same direction. Now you put a pulse at 90-degree pulse along the y-axis, so you will see a motion of your precisional motion uh, to the x-axis, and here you have introduced about 90-degree pulse and 90-degree pulses and 180-degree pulses, right? So I'm not going deep into the thing because Sir has discussed already these things. So here you have also been introduced that when this uh, so it is actually better explainable by the presentation, means slides where those are pictures are there. So but I do not have them right now, so I can't really explain them well, but you can understand that when now along the y-axis some energy is being some so your radio frequency wave that has been so that is applied at such a way that the magnetic field generated from that will actually orient along the y-axis. So that is B1, and due to that presence of B1, it will come to from Z, it will come to precise over that B1, and it will come to x-axis where your detector is along with. And then then what you need to do, then you will turn off your radio frequency, and then it will try to go back to its equilibrium position using a spiral motion along um, spiral motion along the xy plane, and ultimately it will again its z component will uh, increase, or you can say the z component will increase from 0 to some the previous value what you have seen. So in this context you have also learned about spin speed, spin lattice relaxation, and spin relaxation. So this relaxation, the spin lattice relaxation, also the time, you know this is tau 1 and denoted as tau 2. Actually, the application of this spin lattice relaxation come actually, it will give you a idea of the surroundings, the magnetic property of the surroundings. So you know that means apart from detecting the nuclei, another application of this NMR spectroscopy lies in, right, in MRI, right, MRI machines, right. So there the actually the surroundings, like in what is the different tissues of our brain can be imaged using this spin lattice relaxation time. And there is another thing is called spin relaxation. You have also learned that to get the spin lattice relaxation there is an spin recovery relaxation method, right, spin recovery relaxation method. And it follows a equation something like I in intensity is I infinity 1 minus 2 into e to the power minus t by tau 1. And for spin relaxation, which is also known as spin echo, right? Uh, this thing actually means understood by first you give a 90-degree pulse. So that is 90-degree pulse along the y-axis by a radio frequency. So now you turn off that for some time. Then you apply. So you give it some tau time for spin relaxation. Now again you give a 180 pulse, 180 degree pulse. Why? Because along the XY direction, because of the your inhomogeneity of the magnetic field, as well as the your uh, precessing capability or speed of those frequency of those your nuclei, the same nuclei, but they might have different environment. Due to that, they can have a different um, positional motion, and that's why you give them a 180 pulse. So your again whatever change was the span was there in time, that will again be that for to you can say to pay for that means, or to make it even, I mean suppose they were splitted in time or they in space or something like that, and then you put a 180-degree pulse such a way that uh, they will just change their they will rotate something, and now the difference will be gone. What I'm trying to say is, suppose this is your XY plane, and just after some time, you are giving some time, so it came to XY plane. Now you release it for tau one time. Now suppose your which was rotating, preceding fast, it is coming here. This is suppose fast and it is slow, and it is going this side. Now when you apply a 180-degree pulse again, now what will happen, that it will go to your fast will go here, and your slow will come here, and now it will, instead of going from to other direction, it will come together, and that will actually coincide same, and you will get the suppose at first the intensity was something like this, and there will be some loss due to spin relaxation, and you will get something spectra like this, and which will give you a actually a exponential thing, and from there you will get your tau 1, tau 2 actually, the spin relaxation. And for spin lattice relaxation, it was, you will give a pulse 180 degrees, so it will go to the bulk magnetization vector will go to the z, opposite minus z, and then it will uh, to and as your detector is in the x direction, so you give it some time to relax now, and then you put a 90-degree pulse, so that you get the component along the x axis to get something what is the value was there. So actually these things are really very complicated. Professor Datta tried to explain it in a nice manner, so brief manner, so that you can understand these things. I hope if you have any question, you will put that into the discussion forum as well as. So now let us go to actually the 11 week 11 assignment problems. Okay. So now the first question is, the NMR spectra are observed from nuclei whose spin angular momenta, actually the spin angular momenta, your IZ or I, suppose when I means suppose along the Z axis it is IZ, and that is actually MH cut, right? MS, actually not MS, MI suppose, okay. Now you, if your nucleus spin is 0, then your IZ is going to be 0. Then you won't have any NMR spectra, right? Because your that will not be a NMR active, right? So NMR spectra are observed for nuclei for integral, half integral, or non-zero or zero. So actually the answer is non-zero, because for half integral obviously you will see something, for integral obviously you will get something, for zero you won't see anything. But the thing is that as it is a MCQ question, only one option is correct. So non-zero actually will deal both the thing, right? Half integral and integral. So this is the case. Now the second question, a bigger magnetic field in the NMR spectrometer is associated with, as you have know that your if you so I have shown something like this, right? This is your degenerate state alpha beta. Here your alpha will be stabilized and beta will be destabilized. Suppose you are increasing beta. Now suppose when you are increasing this beta, your splitting is going to be high, right? So your delta E is actually dependent on your beta. Okay. Sorry, not beta. So that is actually your B. That is your magnetic field along the z-axis. So actually you can see that your delta H is nothing but H nu L. That is your normal frequency. So as you increase the B, you expect a greater normal frequency. Obvious. Now are you going to expect a greater spin-spin coupling? No. There is no effect on spin-spin coupling by the magnetic field. And what about the first order spectra or the second order spectra? First order spectra you are going to observe, because you are going to observe a spectra where these are much more resolved spectra you are going to see. So there will be less complication there due to the coupling. Uh, that is, the coupling amount will be same, but the much better resolution will be there. That's why you are going to see a first order spectrum. And what about the question number 3? In a FTN, actually this question come from, actually should go to the week 12 assignment, but as it was there in a FTNMR spectrometer, what are the things correct with the given statements? Measurement is in frequency domain. No, the measurement is done in the time domain. So the first option is incorrect. What about the second option? The magnetic field is constant. Is it correct? See here I have the FID thing, I written free intensity decay. Actually it is free induction decay. Okay. So let me correct myself here. I will just erase this thing as it will be there. So I will just correct myself here. The induction decay. So yes, the free induction decay is observed, right? What about your magnetic field? External magnetic field, is that constant? Yes, that is constant. Bz along the z-axis. You change actually your B1, not Bz. Now what about, that is also not changed. Actually it is the amount is same. Now what about the relaxation times? Yes, the relaxation time can be measured using an FTNMR spectroscopy photometer. The first option is not correct. Other than that, all three are correct. Now, what about the fourth question? This also should go to, as we have discussed, or you have read the week 12 assignments or the week 12 lectures. It will be easy for you that 180-degree, then some time, then 90-degree pulse sequence is actually what? This is actually a spin lattice relaxation. Measure the spin lattice relaxation, right? First, you put a 180-degree pulse along the B1. Means first that. Uh, Now you give it some time. Now you again put some 90-degree pulse to get some value or some amount in the detector along the x-axis. So that is actually your spin lattice relaxation. Now what it actually other things, it is not an spin relaxation, right? So I'll cut this. What about the inversion recovery? Yes, it is associated with the inversion recovery, and the formula I will write again. It equals to I infinity, means time infinity, uh, 1 minus 2 into e to the power minus t by tau 1, which is a spin relaxation time. Relaxation time. Now, is it associated with the spin? Actually, no. Your spin relaxation is actually associated with spin ego, but spin lattice is not. Now, what about the question number 5? The proton NMR spectrum of HD. This was the question I was talking to you about. Your proton NMR spectra of HD consists of a what? Singlet 1:1, 1:1, or 1:2:1. Now you use that 2Ni plus 1 rule. Okay. Now we can see that for deuterium, the I is 1. It is an integral 1. So you expect, how many lines do you expect for proton at H? You are going to expect 2 into how many deuteriums are there? 1. And what is the nuclear spin? Is that is 1 plus 1. So you are going to expect 3 lines. So it can be either 1:1:1 or 1:2:1. Most of the student will go is to 1:2:1 because you have learned till now that an equivalent proton, non-equivalent proton will split that singlet proton into a doublet or triplet AX2 system in a AX2 system. But in this case, actually, you are going to see that your deuterium is going to split your singlet into a triplet, but uh, all the intensities of those lines will be equal, 1:1:1. Now the next question is question number 6. Which of the following nuclei are NMR active, inactive? So you have already learned those nuclei. So actually, this is an thumb rule, or you can say this is a shortcut method, that those nuclei where uh, the atomic mass and atomic number both are even, those will be NMR inactive because their nuclear spin, or you can say the nuclear angular momenta actually is going to be 0. So those are actually your 16 isotope of this oxygen and 12C. Okay. Now question comes last question, that is question number 7. What does it say? In formaldehyde, only one proton NMR or 1H NMR line is observed. Why? So what is the structure? It is actually H C H, something like this, right? So actually both of your protons are attached to who? The same carbon, carbonyl carbon, right? Now those are equivalent. So what should they do? Will they couple? Or not? Means will they couple or not? They will couple. What that is what we have learned from the A2 system, right? So chemically equivalent protons will couple, but that will not show it into the NMR spectra. So what about the first option? Two chemically equivalent protons do not coupled with each other. So they do couple. So this is actually a wrong statement. Now the second statement, the two chemically equivalent protons couple with each other, but it does not show up in the spectra. That is an correct option. What about the third option? You already know this is an MCQ question and this is right. Let us see what others are saying. The statements are, so the coupling is offset by shielding by the proton of C double bond O carbonyl carbon double bond. Actually, it is not. So it is also a wrong option. What about the third? That the protons are labile and exchange rapidly with solvent. This is not an example of those labile protons. Protons attached to oxygen or other heteroatoms like nitrogen, there you will see this labile protons case, where instead of a proper singlet, you are going to get some broad signal, which is actually a singlet but single peak, but which will actually be very broad in nature. Anyway, now let us see. Now we'll try to solve. So these are the questions coming from week 11. Now we'll again go back to the basics of our whatever we have learned from the day week 1 itself, and we'll try to solve some numerical problems. This time, earlier I have done some solving of some numerical problems from the Manuel book. Now I have chose the Atkins book, and we'll try to solve. So I will choose. I have chosen in two questions, two equivalent questions actually. So I will solve one, and you will try to solve another one, so that uh, there will be some question that you can solve. Okay. Now let's start with the first question. So the first questions is actually about the absorption and absorption spectroscopy. We have electronic absorption spectroscopy, where you have learned that actually, let us recapitulate a few formulas. Your absorbance or optical density, generally called also known as OD, okay, or absorption, you can also say AB, absorption is, or A is actually logarithm of your intensity of the incident light by intensity of the transmitted light, and this is also equals to epsilon and A at a particular lambda, right? Epsilon, this is a molar um, absorption coefficient. Sometimes it is also known as a molar extinction coefficient, epsilon of lambda into your concentration into path length of your cell or the cuvette you are using. So let us see this with these um, equations, can we really solve this question? So what is given? It is given that epsilon for lambda is equal to 540 nanometer is given. That is 386 decimeter cube mole inverse centimeter inverse. So guys who or girls who are from physical chemistry background, or obviously from chemistry background, you should also know this decimeter cube is nothing but also liter. Okay, so you can go with decimeter cube, but it is also known as liter. So that is a easy way to remember also. Anyway, so the question is, when the light of wavelength passes through a 5 millimeter cell, so it is also given your path length is given, right? So your L is given. L is 5.00 millimeter. So let us convert that to in centimeter. That is 0.5 centimeter. Okay. Now your L is also given. Okay. So going proceed further, let me also check if the thing is being recorded or not. Yes, it is being recorded. Um, now let me go back to the presentation file. Okay. Now it is also given, and what else is given? That uh, cell containing a solution of solute, 38.5% of the light is absorbed. So 38.5%. So your light absorbed is actually IA by I0. So that is being absorbed, into 100%. That is given as 38.5%. So you know what is your IA by I0? This you know, that is your 0.385, right? Now when you my deduct this from 1 both the sides, you will get 1 minus 0.385, right? So you are going to get I0 by IA by I0, and here you are going to get 0.615, right? So your numerator, if you closely see, that is nothing but your now the intensity of the transmitted light of, remember these are all dependent on the lambda, and here the lambda we are discussing about 540 nanometer. Okay, now this is actually your 0.615, and what you already know the formula, that your logarithm of I0 by IT, not IT by I0, is epsilon CL, right? Obviously because your I0 is a greater quantity than IT. So your this log will give you a positive quantity, and these epsilon CL all are positive. So by that way you can also remember this, if it is log I0 by IT or log IT by I0. So it is actually log I0 by IT. So it is log 1 by 0.615. Your epsilon is given 386 decimeter cube mole inverse centimeter inverse. Okay. Into C concentration, we need to get what is the molar concentration. That is our goal is C, and L we know that is 0.5 centimeter. So now your C is logarithmic of 1 by 0.615 divided by your centimeter, and centimeter will cut, so it will 386, and when we will take this thing here above outside, we will get mole decimeter cube minus, that is mole liter inverse, that is your, actually we can write this also as molar, right, something like this. So let us see what value we will get. We are going to get a value of, actually I have already solved this, so I will give you the value that we are going to get 1.094 into 10 to the power minus 3 molar, or you can say mole decimeter minus 3, and this is actually nothing but 1.1 millimolar, you can say, or you can say 1.1 millimole decimeter minus 3, right, something like this. So this is your answer. So I will just highlight this. This is how you can solve this kind of problem. Now I'll go to the next question, and you will see the question reads the same. Instead of 540 nanometer, now it is 440 nanometer. But you see that it is none of this is not an important thing. The thing is that epsilon is given. This is your epsilon, right? So your epsilon is given. Your path length is given. Convert it to in centimeter. Now here your thing is said that I A by I0 is 0.483. Okay. Now using the previous method, I mean expect that you can get the concentration, right? We have already found out concentration formula is log I0 by IT by epsilon into L, right? That I hope you will be able to solve this by yourself. Okay. Now let us solve another question, similar kind of question from this absorption spectroscopy. The question is that the following data were obtained for a absorption at 450 nanometer by a dye in carbon tetrachloride the solvent when using a 2.0 millimeter cell. Calculate the molar absorption coefficient for the dye at the wavelength employed. So we have been given in a table that what is the dye concentration and your transmittance curve. Okay. So if I try to, actually your transmittance curve will be just opposite to your absorbance curve, right? So I will try to draw this. So this is your wavelength into increase this way and transmittance increase this way, right? So actually your transmittance increase this way, opposite. Very sorry. So it is said for the fast concentration, see the concentration is very less, 0.001 mole per liter. You can say that is your 1 millimolar, right? So for that your what I'm trying to do, and I will try to put wavelength. Wavelength is given 450 nanometer, right? Suppose we are measuring at this one. So and these are your transmittance value. So for the fast case, the transmittance is very high, something like this. And suppose this is the maxima. It might not be the maxima, but suppose the way I am drawing, it is the maxima at 450, and it is given that for the fast one 0.001 molar. It is like this. Now I'll choose a different color. Yellow is actually a bad color. Let me choose other. Now, when we increase the concentration to 0.05, see your transmittance percentage has decreased. So, what you expect that it is decreased to this, right? It has been decreased, right? So, this is your 0.05 molar, right? Now, when it went to 0.01, it has even increased, decreased the transmittance percentage, right? 12.7. And it has been said when you went to a 0.05 molar, then there is very less transmission. This is around 0.3 into 10 to the power minus 3, which is very, very less, right? Comparing to this. So, but what do you expect? Should your epsilon value, what does your epsilon value depends on? Let us see. Your formula is something like that, right? Log I0 by IT, right? Is epsilon into C into N, right? Your L is fixed, your C is being varied, and your suppose as the transmittance is changing, so your absorbance will also, what will happen if you increase the concentration, your absorbance will go high as your transmittance is going down, right? So, and suppose you are measuring at a particular lambda, right? So what do you expect at first? That should your epsilon value change? It should not. As you are increasing the concentration, actually your that is actually playing a major role. Your epsilon is actually dependent on lambda, not concentration. Actually, it will be dependent on your concentration if some ground state reaction, or suppose due to high concentration some aggregates form, then the species will itself change, right? Then your epsilon value may change, but the concentration given here, actually you won't really see any concentration dependence. So the first thing before doing the thing, we expect that your epsilon value should not change, right? Now let us solve the question. For the first case, suppose I will write it in a tabular manner, okay? Whatever is given. So these are all given in a percentage, right? IT. So the transmittance percentage, right? For the first thing I am calculating. There are four cases is given, right? Now what are the four cases? The concentration is 0.001 molar, 0.05 molar, actually 0.005, and this is actually 0.01, this is 0.0. Now it is being 0 point, actually it is 814, which is 0.356, and it will be 0.127, and it will be 3 into 10 to the power minus 5, right? These will be in decimal. I'll go back to the here to stay in the call. Okay, let me come back. Now from here you can do the flipping of this, right? Next step will be I0 by IT. So that will, if you reciprocate it, it will get something like 1.229, then 2.81. As it is decreasing, its reciprocal will increase, right here. 7.874. Then it will be very high. 33,333.33. And next we'll get the logarithmic of this value, that is your absorbance. You will see you will get something 0.09 for this case. Now as your concentration is increasing, your absorbance value is also increasing at that particular wavelength, that is 450, 0.896, and then 4.52 for this case. So when you take the logarithm of this value, we are going to get this. Now what next? Your epsilon, and epsilon is nothing but this absorbance by C into L. L is given. L is 0.2. Here in centimeter it is 0.2 centimeter. C is already given from up, right? So you are going to see a value. I will directly write it here for the 7.8. Next, you for this case you are going to see a value of 449, and then you are again going to see a value of 448, and again you are going to see a value of 452. And remember, for all these case, there will be some unit. Unit is, what will be the unit? It will be the reverse of the concentration, and unit and reverse of into multiplied by centimeter inverse, right? So that will be mole inverse centimeter inverse, or you can say mole decimeter minus 3, or mole inverse decimeter cube centimeter minus 1. Okay, and you can see right now, see your epsilon value, what we have discussed till now, that your epsilon value didn't really change, or it is almost 448, 449, 452, and some changes is there as you have changed the concentration very high. 0.05 molar is actually very high. If you are getting an absorbance of 4.52, you can see this is in logarithmic scale, so it's very high concentration. That is why you can change a little bit, that not too much, and that is not due to the aggregation. Don't think about that. If you some aggregation is happening, so that aggregate is a new species, and it will have a totally different epsilon value. It may be close, but generally the epsilon value, I think, simply decreases. Okay. Okay. So as we are solving this problem, so I am giving this you as a homework, whoever is watching this video. To the question says the same. A table is given, concentration and transmittal percentage, absorption at 600 nanometer is being recorded, transmitted, and the cell size, the path length has changed, 2.5 millimeter, that is 0.25 centimeter, right? And I hope you will be able to solve the same thing, and I hope you will get the same value of epsilon from there, right? I hope you will be able to solve that. Okay. Now move on to the next question. That is from rotational spectroscopy. Now, okay. So the question says the calculate the frequency and the wave number of the J223 transition in a pure rotational spectrum of 14N 16O. The equilibrium bond length is given, which is 115 picometer, and so we need to calculate the frequency and the wave number. And it also wants to know, would the frequency increase or decrease if the centrifugal distortion is being considered. Firstly, we will try to solve this problem as a rigid rotor. Now centrifugal distortion will come into play when we assume or a real case where actually these atoms or the bonding is actually not a rigid rotor but a non-rigid rotor, right? So first we will solve this problem as a rigid rotor, and we will first recall that um, what are the formulas there for rotational spectroscopy. Okay. So the rotational constant B, right? That is H by 8 pi square mu r square C, and usually if you choose this, you are expecting this to be in centimeter inverse, right? H is Planck's constant, mu is your reduced mass, r is the bond length, C is the speed of light in vacuum. Okay, that is your rotational constant. What about the individual energies of a rotational level? In centimeter inverse, it is B into 2B, sorry, B into J plus, wait, I will erase the eraser, use the eraser. B into J plus 1 centimeter inverse. Actually, it will come in a centimeter inverse because B has a unit of centimeter inverse. So that is one thing. And what is the gap transitional energy will be there? Suppose, or what will be the energy for E2? 2B into 3, that is 6B. What will be the transition energy for 3? That is 3B, not the transition energy for that rotational level, 12B. Actually, the gap will be 6B, and you already know that it is also, you can also count from this formula, 2B into J plus 1, J being the initial rotational level. It will also give you 2 plus 1, 3, 6B, right? And what we learned, that what will be the gap between individual rotational spectra. Suppose you are going to get for assumption of a rigid rotor, so the gap will be same, will be 2B, right? This is the case. Now let us come back to this question and try to solve this problem. The question says that calculate the frequency and wave number for this transition for a pure rotational spectrum of 14N 16O. 14N 16O. So let us first calculate the reduced mass. So it will be 14 into 16 by 14 plus 60 in 30 AMU, right? And which is nothing but you need to multiply this thing with 1.66 and 10 to the power minus 27 from AME to kg. Okay, and you are going to get a value of 1.24 into 10 to the power minus 26 kg. If you calculate, you will get this. Next, so you understand that to
get the gap, that is 2b, or the 6b, you already know 2b into j plus 1, or actually for j is 2, that is 6b, we need to get the value of the rotational constant, that is b. So let us calculate that. Where is my cursor here? So h is Planck's constant 6.626 into 10 to the minus 34 kg meter square second minus 2, which is second minus 1 joule second. So that will be like that. Now 8 into 3.14 square into mu, that we know 1.24 into 10 to the minus 26 kg, right? Now comes the R. R is here the bond length, that is 115 picometer. This picometer is actually 115 into 10 to the power minus 12 meter. Minus 12 meter. Okay. Now you need to square those, and C I will take in centimeter per second. Okay, 3 into 10 to the power 10 centimeter per second. As you know that by solving these problems that if you need B in centimeter inverse, so I kept like that. So kg will cut, right? Meter square will cut from the here, right? Meter square. Now, second inverse will cut from here. Your centimeter will come as a centimeter inverse, right? When you do the calculation, you will get a value of B as 1.7075 centimeter inverse. Okay. So this is the value of B you are going to get. So what will be the wave number? In wave number, that is of, and same thing, delta Ej 6b, right? It will be 6 into 1.7075 centimeter inverse, which is nothing but I think 10.245 centimeter inverse you are going to get. So this is in wave number, right? You need to also calculate the frequency. So wave number is nothing but 1 by lambda, right? So you need to multiply this by C. To get the frequency, you need to multiply this by 10.245 centimeter inverse into 3 into 10 to the power 10 centimeter second inverse, right? So you are getting it in hertz. So for this, you are going to get something around 30.735 into 10 to the power 10 hertz or second inverse, you can say. Okay. So now this is your frequency of of this transition, and this is in wave number, right? Now, what would happen if we bring together the centrifugal distortion? What have you learned till now? We have seen whenever we brought centrifugal distortion into the picture, so it was something like minus d into some term was there, right? So actually the gaps, or actually the energy levels when the centrifugal, when it becomes a non-rigid rotor, it actually, for the first one there will be not much change, but with increasing b or increasing j, we will see there is will be change in the, so it will decrease, actually your transition energy will decrease. So you can understand that if centrifugal distortion is there, then your this transition energy what you have found out, that is going to be decreased. So if that decreases, your frequency is also going to decrease. So the answer will be frequency will also decrease when
your centrifugal distortion is being considered.
I hope you got a recapitulation from the rotational spectroscopy from this question, right? So I will go to the next question, which tells the same thing, but uh, the thing is that you have to calculate the frequency and wave number for the transition J1 to 2 in a pure rotational spectrum. Now your molecule is 12 carbon, 16 oxygen. So you need to calculate the mu, reduced mass, convert that to kg. Now equilibrium bond length is given that 112.81 in picometer, convert that to meter. And again you use the similar argument or similar equation to get the wave number or the energy gap in centimeter inverse. Then multiply by the velocity or the speed of light c to get the frequency. And here the same thing is there if you are introducing centrifugal distortion into the picture, then your frequency is going to decrease, right? I hope this problem you can solve it by yourself. Next, let us see what is the next question. Next question is a little interesting because we have not solved any problem till now regarding the, I think we have solved one problem in the assignment regarding the Raman spectra, right? Did anyone join? I got a sound. No, except me, no one is there. Okay, it is what it is. So the thing is, a question is the wave number of an incident radiation in a Raman spectrometer is given. That is 20 point. Actually, is it 2048? Actually, it should be 20.487. Okay. 20 point. So it has converted itself back to the red light. Okay. Where sorry, red light means red ink. Um, 20.487 centimeter inverse. So question is what is the wave number of the scattered Stokes radiation of J 0 to 2 transition for 14 N2? Take B value is already given. So first let us recall what rotational Raman spectra was. So your incident photon was the same as the Rayleigh scattering, right? So this is for your Rayleigh, or here the incident and radiation, which is at 20.487, right? Now where was the Stokes line and anti-Stokes line? Stokes lines, if this is in centimeter inverse, that means in this case um, the energy is actually decreased. If this is the line where sorry, yes, if this is the where the new bar or the wave number is going to increase, then for Stokes shifted line you are going to expect that your Stokes shifted lines will come on the right this side. It may have some intensity, something like that. Let us not go into that. So these will be your Stokes shifted line, Stokes shifted or lines, scattered lines, and here you are going to see anti-Stokes. In case of anti-Stokes, your scattered light has more intensity. In case of Stokes, your scattered light has less intensity. Okay. Now the question says, and one more thing for rotational Raman, what was the For rotational Raman spectra, selection rule was delta J equals to plus minus 2, right? So that's why it is we are dealing with 0 to 2 transition. Don't think about 14N2. You can think about why they have chosen 14N2. Why? So it is, see, 14N2 is a homonuclear diatomic molecule. So for this case, the permanent dipole moment is 0, right? So from rotational spectroscopy, pure rotational spectroscopy or micro spectroscopy, you won't be able to get the, maybe treat the rotational or micro inactive this one. But when you take rotational Raman, then it is a rotational active Raman active molecule. Okay. Now, here what is the energy difference? Let us see. So the energy will be the same, right? For microwave we have discussed, right? Bj into J plus 1. This is in centimeter inverse scale, obvious. And for delta E J, for delta J equals to plus minus 2, you are going to see, you are going to expect here, I guess, 2B into J plus 3. Am I making it correctly? Let us perform and we will understand. So J E J equals to 0 is 0. Epsilon 2 energy of that rotational level will be 2B into 3, that is 6. So it is 6B. And what about this? What will come? 0 to 3? Yeah, it will also. I think we are doing fair job. Let us actually calculate what we can J plus 1. So it will be B J plus 1 into J plus 2. So ultimately the energy gap is E J plus 1 minus epsilon J. That is, we'll take common this thing. We'll take common this thing and we'll get J plus 2 minus J, that is your 2B. Am I doing it correctly? 2B. I think I'm making some mistake. No. Why am I? B into 2 will come from here and J plus 1. No, I am making some mistake. What mistake I'm doing? Actually, J plus 2. I should take epsilon J plus 2, right? Here is the mistake. J plus 2 and it will be J plus 3. So there will be no such common thing will be there. Let me erase this part. B into J plus 2 J plus 3 minus B into actually J square plus 1, and here we will get J square plus 6 plus 5J minus J square minus 1, J square gone. So it will be something like J square J B into 6 6 plus 4J, that is nothing but, let us take common 2B
2b, 2j plus 3. So this should be 2j, 2b into 2j plus 3, not j plus 3. So this is the mistake. So it's a good practice to always go and check that. So here we can see the so from 0 to 2 transition, we expect the 6b amount of transition energy or wave number is required, 6b. So what is the wave number for scattered Stokes field for that? And one more thing we need to remember here, that where fall, it will fall 20.487 minus 6b. Okay, because suppose if it was a 0 to 0, there should not be 0 to 0, but as it is a Stokes shifted, I told you that the scattered light will have lesser energy than the incident light, and uh, the the fast line 0 to 2 will be at a distance 6b lesser than that of the incident Raman in the centimeter inverse scale. So okay, I will stay in the call. Um, so here it will be, so so you will see the rotational line will takes place at 6 into 1.9987 centimeter inverse. Let me check what this is. Actually this is close to 12. 6 into 1.9987, which is 11.9922. So you may expect your rotational line to be here 11.9922. You can check that. So you expect your rotational line to be here. Okay, 11.9922. What if it was your B value was not given? Your B value should have been given. So you can also check that the gap between this Rayleigh scattering and this is actually going to be 4B, right? So check, is it not to minus 20.487? Actually it is going to be equals to your 4B value. So your stroke shifted line, the fast stroke shifted line actually stays at a distance of 4B as well as the anti-Stokes line also. So this gap you should also remember, this gap is also 4B. And then it is come as a fast line 4B. And am I making the correct statement or am I making any wrong statement? Let me once try to recapitulate. Uh, Now for 0 to 2, and what will be 1 to 2? 1 to 2 will be for this 1 to 2 transition will be 2b 2 plus 3, that is 5 10b. So this is at 6b, so this will be at 10b. I think I'm not making a correct statement. The gap between individual Stokes lines are actually going to be 4b, not this one. Okay.
this gap is actually at 6. Okay. Now, by the similar argument, you can solve the next problem what I have given for you here. Okay, that you can do. Now, what about another question? Rotational Raman spectrum of another homonuclear diatomic molecule 35Cl2 shows a series of Stokes lines separated by 0.9752 centimeter inverse and a similar series of anti-Stokes lines. Calculate the bond length of that molecule. So, see, so homonuclear diatomic molecule, you won't be able to get the bond length from microwave spectra because that is microwave inactive because it is dipole moment, permanent dipole moment is 0. So from rotational spectra, you can see that your 4B is actually 0.9752, right? Just now you have seen that the gap, it will have a gap of um, 4B from each between the each Stokes shifted line, right? So 4B is that. So calculate the bond length. So from here you will get what about the value of B? Let me calculate. 0.9752 divided by 4, that is 0.2438 centimeter inverse, which is very very less. And for 35Cl2 you can know what is the reduced mass for 35Cl2, right? So that is 35 into 35 by 70, 35 into 1.66 into 10 to the power minus 27 kg. Okay. Now your B means B is h by 8 pi square mu r square c, right? So your r is nothing but b into 8 pi square mu c by h to the power half. So it is b is 0.2438 into 8 into 3.14 square into your mu is 35 by 2 into 10 to the power minus 27 into 1.66 into c 3 into 10 to the power 10 centimeters second inverse. Here it is in kg, right? It is in centimeter inverse, centimeter cut. Now h is in 6.626 into 10 to the power minus 34 kg meter square second inverse cut kg cut. So you are getting uh, kg meter square, right? Uh, why I'm getting uh, r and below? Have I made any mistake? Mm, yes, actually I have taken this thing as wrong. R will go here, B will come. So I can take the reciprocal of this also. Not to worry. Minus 0.5, which actually give me. Let us calculate. 24 into 8 into 3.14 square into 35 divided by 2 into 1.66 into 10 to the power minus 27 into
26.626 divided by 10 to the power minus 34. It gives me around a value of 2.5 into 10 to the minus 19 to the power. I am getting a value of R at 1.988. There are some more decimal points are there, minus 10 meter, which is nothing but angstrom, 1.2 angstrom. Sorry, 1.988 angstrom, right?
So you can calculate the bond length from here also. Okay. So I have a similar question like this? Yes, we have. So please do this calculation to get the answer for that. Okay. Now let us uh, calculate or see if I have any other questions. Yes, I have. The question says the hydrogen halides have the following fundamental vibrational wave numbers. That is 4141.3 centimeter inverse for 1H19F, 2988.9 centimeter inverse for 1H35Cl, and 2649.7 centimeter inverse for 1H81 bromine, and 2309.5 centimeter inverse for 1H 127I iodine. Right? Calculate the force constant for hydrogen halogen bonds. So you remember that formula? That is your uh, um, oscillation frequency. Here oscillation wave number is 1 by 2 pi into k by mu. Okay, your k is force constant and mu is actually your reduced mass. Okay, so I will not do this calculation because you can understand that you have what is given to you. So this frequencies, or you can say this wave number is given to you. Okay, so what you need to do, you need to calculate the mu for different halogen hydrogen uh, molecules, and you put them there. So you have W, you know 1 by 2 pi is constant, you get the mu, so you will get K, the force constant for individual, right? That is the first part. What do you require in the second part? So the second part says, from the data in the exercise 11C1A, predict the fundamental vibrational wave numbers for the deuterium uh, halide, deuterium halides. So in this regard, we need to recapitulate a few things. Okay. So from solving the Schrodinger equation, you will get the energy for EV as half this thing, right? Omega at equilibrium or oscillation centimeter inverse, right? When you introduce uh, enharmonicity constant, or you now instead of a simple harmonic motion or a parabolic thing, you means bring to the picture that the uh, enharmonicity thing in that thing, you will see that your energy is going to change in some way. Actually, this mu plus half into the omega bar or something like that. And now you are going to see this part will be there, but in addition to this, you will have some faster correction to that. Means you need to do some perturbation theory calculation, and in this thing will come something like WE is there and enharmonicity constant will come. So this I hope you remember. Now you also remember these vibrational levels have, these are in IR, or so these have higher energy level gaps than the rotational levels, right? Rotational levels in room temperature, many of them can be populated, right? But in case of it was shown that at room temperature, using the Boltzmann distribution and Boltzmann distribution, it was shown that most of the molecules, or most of the molecules will remain in the ground state, that is V equals to 0 state. Okay, so so it will be good if you, so in your spectrum you will observe the spectra for equals to 0 to 1, 0 to 2, 0 to 3, something like that. So these 0 to 1, so let us see what is 0. 0 is half WE minus, these are all in centimeter inverse. Okay, it will come in centimeter on inverse. So 1/4 WE. What about 1? It will be 3/2 WE bar, 9/4 WEXE. Now E2 is 5/2 WE bar, um, 25/4 WEXE. What about E3? E3 is um, 7/2 WE minus 49/4 WEX. So what is the gap transition? So if delta epsilon 0 to 1, that will be, that gap is WE minus 2 WEXC, which is nothing but WE common 1 minus 2XC, right? For delta E 0 to 2, we will get something like 2 WE minus um, 6 WEXC, which is nothing but, if you take common WE, 1 minus 3XC. And if you go for 0 to 3, we'll get 3 WE minus 12 WEXC. That is here. If you take 3 WE into consider common, 1 minus 4XC. Actually, this 0 to 1 is known as your fundamental transition, vibronic transition. This is known as fast overtone, which will be weaker than this fundamental signal. Even weaker will be, or this is known as second overtone. Okay, so you have already your WE values, right? So WE values, so from there you can understand the fundamental vibrational wave numbers from these deuterium halides. Actually, for this question you don't know what is your XC, right? The anharmonicity constant. So you can take them as 0 for this part. Okay. So for this question, you can take them as 0 because anharmonicity constant for this hydrogen halogen bond is not given in the question. So you can take them as 0. Okay. Okay. Now let us go to the next question. The next question says the calculate the relative numbers of chlorine molecules in ground state and the fast state vibronic vibrational state at two different temperature. Again, this will be something like that. I zeroth V equals to 0. Intensity of the population you can also say, right? V equals to 1 will be based on the um, Boltzmann distribution will be delta E by KBT. KBT is your Boltzmann constant, and delta E is here actually E1 minus E2. Okay. So that is also given your in terms of centimeter inverse. It is given 559.7 centimeter inverse. Turn that into joule. Okay. Turn that into joule. You have your KBT. You know 1.3338 into 10 minus 23 joule Kelvin inverse. Put the values of temperature and calculate it. You will see for the, so what do we expect? So at room temperature, what I have said, the most of the molecules will stay in the uh, ground state, right? So in the first case, you will see for T equals to 298 Kelvin, when you do the calculation, you will see it will be P0 by P1 will be 0.0668, something like that when you calculate that. And when you increase the temperature, what you are expecting, that you are increasing the temperature, so your molecule is again having some more energy, so it is going to the fast, and your ratio should increase of P0, sorry, ratio should decrease, right? Or ratio should increase. Mhm. Actually, I am making mistake. So it is actually V equals to 1 to 1 by 0. So that is why it is very less, right? Else it would have been a much more, right? Yeah, that means more than 1, because I told you that 1 is highly, the zeroth vibrational space is mostly populated, and here you expect your ratio to be increased, that is you will get 0.199 at 500 Kelvin. So you can solve these two questions. Below at corner I have given another question of same category. So you can try to solve them. These questions are for Atkins anyway. You will find more questions there. And another question regarding that um, 0 to 1, 0 to 2, 0 to 3 um, transitions are given. Okay. So, okay. So these are given. You need to calculate your new bar and HC. So we already know that for 0 to 1 we are getting and WE common 1 minus 2XC, and that is given as 1556.22 centimeter inverse. Okay. Now we have another 0 to 2, so it is 2WE 1 minus 3XC, that is given as 3088. So this is the first overtone. So your fast overtone will have very less, very, I guess, less intensity than the fundamental, and obviously the second overtone will have lesser intensity than the second overtone. So 0 to 3 delta EV is going to be 3WE 1 minus 4x, and that is also given 4.96.21 centimeter inverse. So you can solve these, right? You can multiply these by 3 and minus. So this is your equation 1, this is your equation 2, this is your equation 3. So you can multiply the equation 1 by 3 and then deduct equation 2. So you will get some for WE you will get. And then put that thing into one of the equations, so you will get X. That is how you get, and your WE is nothing but this new bar. Okay, so don't worry. So this is your WE actually. So this is nothing but your WE. Okay. So actually that is the formula. Actually I remember. That's why I am writing like that. So anyway, so please perform this question and as well as the next one, as you can see the of the similar type of question. You can, I hope you will be able to solve them. Okay. I think this is the last question we have. Yes. Let us discuss that and we'll end our session here. So the question says calculate the percentage difference in the fundamental vibrational wave numbers of these two sodium chloride having two different chlorine isotopes on the assumption their force constant are same. Okay. So same your fundamental, you can take your Xc to be 0, your anormality constant to be 0, and you will get your fundamental is how much? Your fundamental is 2 We, right? Is it? Actually We, right? So I'll use the eraser once. Oh, your fundamental is We. Is actually We into 1 minus 2Xc, anormality constant. It is actually very less. Now for this question, it is not given, so take Xc to be 0. So it is We. And you know your We is already, We is nothing but 1 by 2 pi force constant by your reduced mass. So take the reduced mass for two chlorine isotopes for two sodium chlorides and get that. So you can get the difference in the fundamental vibration, right? You have a ratio of them and you will get that thing. So I'm not doing this calculation, but I'm hoping you will be able to do that. So I hope this was a good session recapitulating all the previous questions. Uh, Hope it will be important for your upcoming exams. And the next week discussion will again discuss the assignment week 12, some numerical problems. Um, Basically, and most of the questions will be from this molecular spectroscopy numerical problem. This question, and I will try to cover some NMR questions, NMR numerical problems, and I hope it will be interesting and helpful to you. And I hope you are watching these videos online as I am recording them. I will meet next time then. Till then, uh, bye bye. Thank you for listening.